I wanted to say a couple of words about the use of the word dogma. It has a slightly negative connotation, but we really wanted to use it in its real sense of dogma is a belief, and it's a belief that you usually have without much sort of reasoning behind the belief. And the reason we wanted to use that word is because we wanted to acknowledge that there are actually some good historical and cultural reasons for some of these, for all of these dogmas, but that they still are beliefs and not truths. And that means that there are assumptions behind those beliefs. And we wanted to explore what those assumptions were, what led to them, and also what were some alternatives to those assumptions that might move us away from those beliefs. The last thing we wanted to do was to set up a sort of pendulum swinging where we go from one side of the belief to the opposite side. So we're really trying to explore the continuity of different sort of assumptions and how they might lead to different kinds of actions and theories that we might take in mathematics education. So we're not here to convince you that mathematics is never a building block subject or mathematics is never hard, but to see why people say that and believe that, and what are some other options. So as I said today, I'm gonna start right now with this belief that math is culture free. Maybe those of you who are sitting here don't think of that, but I'm sure that you've heard teachers and students and other people that you've encountered in everyday life claim this. And we wanted, in the book, we explore it a little bit, and I'm going to share with you some of our ideas around rethinking that dogma. In the book, we have a story for each one of the dogmas, and I know that last week Alf left you with some spatial imaginations that he invited you to do, and he said that maybe that would be the main thing that you would remember from his talk, because we tend to remember the things that we visualize. But I think another thing that we remember as humans are our stories, and so I hope also that these stories can be ways for you to remember some of the ideas in the book. So I invite you, I can't see you, but I invite you, if you'd like, to close your eyes while I tell you just a short story related to this dogma. So a few years ago, I was working with some elders from the Nuu-chah-nulth First Nations, which is located on Vancouver Island in British Columbia, where I live. And we were translating numbers into their language for the Touch Counts iPad application that we were designing. This was not an easy task because the Nuu-chah-nulth people were forced to give up speaking their language in the residential schools that were set up by the Government of Canada, which means there were now very few fluent speakers left. Also, there are variations of the language that depend on specific geographical locations. Those who lived along the sea used numbers differently from those who lived along the river. This meant that some of the larger numbers, like 60, are said differently by different elders. I was intrigued by the different meanings that the number names had. For example, the word for 9, which is kawakwal, means 1 less than 10. I was asking the elder whether the word 7 had any particular meaning. The elder started making a pinching gesture with her thumb and index finger and mentioned plucking the feathers of a chicken. I was astounded, finding it hard to believe that chickens and 7 had anything in common. She then started counting from 1 to 10, both out loud and with her fingers. And all of a sudden, it all made sense. The gesture accompanying 2 was a pinching gesture on her right hand, and the gesture accompanying 7 was the same pinching gesture on her left hand. In Nutshalt Nuth, the numbers 2 and 7 have a symmetry that is completely missing in the English language, and their accompanying gestures are inextricably linked with a specific cultural practice of plucking chickens. But the story is not over. After the elder finished counting to 10, she told me that she had not done that since she had been 8 years old, when she was sent to residential school. It was an emotional moment for her and for me. It was also an incredible testament to the strength of the memory of her fingers and to the fact that numbers are much more than symbols, much more than words. They are furling up in our experience of life, painful as they may be. Numbers are objects we use to count and calculate, but they're also specific ways of moving our bodies. So I'd like to share with you a short video clip of the elder so you can see for yourself the way she moves her fingers and also hear how she speaks the numbers.
Okay, Tawak, Atla, Atsa, Mu, Sucha, Nupu, Atpu, Atakos, Tawakot, Hayu. Okay.
Okay, so why is it hard to believe that mathematics is culture free? Well, we can see, I think, very clearly in the story that mathematics involves language, bodies, and the land. Here in the video, we see the language that articulates this symmetry between 2 and 7, which is very specific to that culture. And not something we have in English. I look forward to hearing how you say those numbers in Polish. We can see that the particular ways of counting with the fingers, so different ways of moving the body, also quite specific to that culture and not something that I've ever seen in any other culture. And finally, there's the connection to the ways of counting to everyday practices. So here, the connection to plucking the feathers off of the chicken. So already we see how mathematics is intertwined with language, bodies, and land, and not somehow separate from that. All of these aspects that we see in the video here have some commonalities across all cultures. So all cultures count on their fingers. That is actually true. Every culture that has ever been documented counts on their fingers. All cultures have unique names for numbers, such as 2 or 7. And all cultures are involved in some kind of farming or animal practice. So in that sense, there's something that's shared across, but there are also some interesting difference across those cultures. So different meanings of the words, different ways of using the fingers, and different farming practices. And for me, this is a nice way of seeing how mathematics occupies this very interesting place in our world, where it somehow does seem global, but it also is very local. So at the same time, being both global and local and not just one or the other. So we have in our book a few different ways of talking about how the cultural aspects of mathematics can be made more evident in the classroom. One of them is about exploring language, and we give the example of the word in Turkish for multiplication, which is katma. And that word actually means to hit. And in Turkey, the way that multiplication is taught is really through the Cartesian model. So there's no distinguishing of one factor, the multiplier, from the other, the multiplicand. And this word carries a lot of the meanings for multiplication, which again is very different than what we would have in English or in the Romance language. languages. So exploring those words for their meanings and their particular cultural meanings is a fantastic way to help students and teachers see the cultural specificities involved in mathematics. Another example that we give relates to measurement. So again, all cultures have and continue to use their bodies as ways of thinking about measurement. In English, maybe you've heard of the foot, which is one of the important measurement systems, which actually means the king's foot. So there are small parts of the bodies that are used there, but there's also arm span, which is another way of thinking about measurement. There's also more mobile ways of thinking about measurement, like the indigenous people in the East talk about a stone's throw, or about the number of coffee breaks needed to go from one place to the other. So all of these embodied cultural practices that are built into our ways of thinking about and using measurement can provide another way for students and teachers to see the cultural aspects of mathematics. And finally, I'd like to talk today, focus on some of the axiological dimensions of mathematics. And by that, I mean some of the aesthetic and ethical aspects of mathematics that we often don't make very present in our mathematics teaching. So in order to highlight some of those, I'm going to talk a little bit about values in mathematics. So values include both our aesthetic values, what we find beautiful and ugly, and our ethical values, so what we find right and wrong and so on. I'm going to focus mostly on some of the aesthetic values, and I just want to give you a sense of how mathematics is shot through with values by providing a few examples. One of them is in the book by Lakatos, where he shows us the emergence of the formula V minus E plus F equals 2. We can see very clearly how that value of coming up with a simple property that can apply generally actually drives the whole mathematical work on coming up with a definition for a polyhedra, which is the polyhedra is the shape that must have this property of V minus E plus F equals 2. And Lakatos in his book shows several places where the mathematicians and the students are alpha and gamma are arguing with each other because they don't think that this is an adequate way to define the polyhedra. They want to include more polyhedra, but if they did, then they wouldn't be able to use this formula. So I think it shows this tendency in mathematics to want to come up with properties that are as simple as possible and apply to as many situations as possible. That's not something about truth. That is really something about aesthetic values. A second example I think we can see in prime numbers. So the desire to come up with a small set of underlying generators. So in this case, the prime numbers are the ones that can generate all of the whole numbers. And this is a tendency that we see in many other areas of mathematics, in linear algebra, for example, of mathematicians working to find the small set of objects that can generate everything. We can see it too, I guess, in the axiomatic system. Again, this is a value. There's no reason why it has to be the smallest set, but it's something that mathematicians strive for. And my last example is the Langlands program. So this is a program that is very operative today in contemporary mathematics that seeks to make big connections between different branches of mathematics. And many mathematicians are now working on trying to show different aspects of the Langlands program. And what this shows to me is, again, a desire to take disparate areas of mathematics like algebra and geometry and to figure out bridges that work across. And the fact that this motivates so much work in mathematics shows how important this value is. Of course, since they're values and they're connected to human language and body and land, they change over time and across cultures. So just looking back a couple thousand years, we can see those major differences operating across cultures. So in India, we saw a strong focus on calculations. The Indians were superb with their calculations and valued very much coming up with extraordinary calculations. Whereas in China, we saw a strong interest in visual demonstrations, which is quite different than what was happening both in India and in ancient Greece. And it's a value that we see percolating through to today in different cultures. And finally, physical forms of argumentation that you can see in the work of Archimedes that was later banned by mathematicians like Descartes and also modern mathematicians like the Bourbaki. And so here we can see again places where different values, different preferences and ways of thinking come up in mathematics that are not independent of the mathematics itself. So let's look at a small example here in the context of problem posing. So about 20 years ago, I developed a little program called the Color Calculator. It looks like this. As you can see, there's a calculator that looks like any other calculator. But what you can do is to input a fraction. Here, there's the fraction 1 over 124. And unlike a normal calculator where you'd only get 8 or 9 decimal values, here we get a whole bunch of them, up to 100, but we also get a visual display of those numbers. And with that visual display, we might see patterns that the string of numbers don't make that obvious. Here the table, so the width of the table has been set to 15, which makes one of the patterns in this decimal expansion particularly visible. So I'm going to ask you to open that URL in your browser right now. So it's at tinyurl.com and /color calculator. And I'll give you a second to do that, and then I'll open it myself so I can talk a little bit about it. Okay. So here I have the same, but I haven't put a fraction in yet, so I don't see the visual display. Maybe I'll put in 8 over 7. But I invite you to put in whatever fraction you'd like. So I click the 8 and then the slash and then the 7 and then the equal button. And I get this display. So I can change the width here to 11, for example, or to 12 and so on. So I would like to invite you to experiment with a few different fractions, and then I'm going to ask you what kinds of things that you noticed. So I'll give you a minute or so to experiment.
Yeah, hi. Hi. So I'm Harita. I try to see 8 by 3. I wanted to ask when there's a numerator bigger than the denominator, and if you change the column sizes, it's giving very different pattern. And if you just reverse the fraction, like 8 by 3 and 3 by 8, like it's very differently. And one of the question I also wanted to ask is, how do I have like, as you have already mentioned, in Indian system, we also have this, you mostly write 1 complete 2 by 3. Is there any chance I can write a fraction like that in this one, or no?
No, we only have numerator over denominator. So you would have to convert it to an improper fraction if you wanted to do 1 2/3, for example.
Okay.
Yeah.
Okay.
I want to just stick with what you said. I've never seen that before, which is quite nice, which is that you tried 3/8 and then 8/3. Yeah. And you were looking to see what kind of different patterns that would happen with those fractions. Thank you very much.
Yes.
Okay. Let me go back to the to my PowerPoint. Okay, so what I hope you experienced if you tried out any of the fractions was shifting the activity from calculating answers to the fractions, so trying to figure out what 8/3 is as a decimal number, to working on generating new objects and relationships. So in the example that we saw is the relationship, for example, between 3/8 and its inverse. And you were doing experimentation and then getting feedback from that experimentation, not through the teacher, but through the color calculator itself. And of course, the visual patterns were a very important part of your experience with it. So trying to see which patterns were different. So I'd like to share with you some of the questions that a group of grade 7 students asked. And this comes from a paper that I wrote 22 years ago. And so in the first one, for example, how can I make the diagonals go in an opposite direction? So we can see from the picture here, the student had a picture that looked a bit like the top here with the nice columns. And their question was how to make it look like the second picture underneath as going for diagonals. So we can see here some problem posing that is based on the student's interest in columns and diagonals. That's a problem that would be very difficult to pose outside of the context of the color calculator. Another question I just wanted to highlight, the decimal stops when there is 2, 5, and 10 in the denominator. I wonder what happens with 8. So here we're noticing, the student is noticing a pattern, and in particular, the fact that those decimal numbers stop, which is unusual kind of pattern to notice because we most frequently give students fractions where that is exactly what happens, the decimal stops. And here the student is realizing that with most fractions, it actually doesn't. So interested in the idea of it stopping and continuing. And then finally, draw your attention to this last one. I want to make the table all red. So this is coming really from an interest in sort of getting all of the numbers to be not just the same, but to be red, so a very particular color. And again, this is a question that we could ask outside of the color calculator, but who would ask, I want to make 0.33333333? Of course, it's much more interesting of a question to think about making it all red. A couple weeks ago, just as I was preparing for this talk, I received some new work from students, also in grade 7, who had worked on the color calculator. And I wanted to highlight it here because it shows yet other explorations that these students made. So in this case, the students were interested in looking at the particular denominator of 7 and noticing the cyclic feature of the decimal numbers as they went from 1/7 to 2/7 to 3/7. In this example here, the students were interested in comparing the length of the decimal in moving to different denominators. So starting with 7, but then moving 33, 46, and obviously an interest in trying to make the pattern go as long as possible. And finally, I was very interested in this one because the student found a fraction that didn't have a repeating pattern, at least in the first 100 digits, and found this fraction 3/708. And I find this fascinating in part because 3/708 is such an arbitrary number that you wouldn't encounter normally, yet it's one that became special for this student because they were able to not have to focus on calculating it, but looking for patterns around that fraction. So in the book, we talk about, we have different spatial imaginaries that we try to use to help communicate some of the differences in dogmas. And so I think that most people think of mathematics more in the context of the diagram on the left, which we call inside-outside separation. And in this image, mathematics is in the center, somehow sort of intact and separate from layers like language, like history, like technology. So the idea here that many people don't even articulate explicitly is that mathematics is somehow separate from these other cultural ideas, that they get layered on to some kind of atomic mathematics. And you can see that in a lot of the ways that curriculum are written, and even in many of the ways that our theories in mathematics education are written, where we add the social cultural part to the mathematics. On the right, we have a different spatial imaginary here, where mathematics isn't at the center at all, but is kind of shot through with history, technology, language, and there may be more things to add there, but where the very fabric of mathematics is itself intertwined with its history, the technology, and the language. And we have this graying out around the side because there are certainly parts of mathematics that seem to have more overlap across different cultures. So that would be sort of in the middle here where it's quite dark. And then other parts of mathematics that have quite a bit of overlap that differ across different cultures. So that image there is trying to capture more of a continuum rather than a layering. So in the context of the color calculator that we were working with, we see these, I wanted to highlight the role that the values played in engaging with the mathematics. And so some of the preferences, some of the things that you were attracted to in terms of the color, in terms of how the fractions worked, are all part of the making of the mathematics and not somehow separate from it. Okay, so now I'd like to turn to the second dogma that I'll talk about today, which is mathematics is always right or wrong. And in our book, we talk about the different kinds of truths that have emerged around mathematics historically, starting from the ancient Greeks, and then the big shift that occurred with the discovery of non-Euclidean geometries, and then, of course, Gödel's incompleteness theorems that really changed how mathematicians themselves thought about truth. Today, I want to start with another story. And so again, without falling asleep, if you want to close your eyes while I open this dogma with a second story. When I was 9, I remember riding in our pickup truck, squeezed between my parents in the front seat. I asked my mother how far we were from our destination, and she read off the distance from the map in miles. Canada had recently converted from the imperial system to the metric one, but our maps were old. When I asked for the kilometer equivalent, she responded at what seemed to me like lightning speed. How had she done it so quickly? I knew that conversion involved multiplying by some complicated number, not a whole number, as my teacher had drilled us for years prior to the changeover with equivalence charts and rules. So I believed this wasn't something you did in your head. And shouldn't she have needed some kind of pencil and paper or even a calculator to do the conversion? She soon explained. There was no need to bother with the actual conversion factor, something like 1.609, Instead, you just rounded to 1.6, which was just the same thing as 1 plus a half plus a tenth. And that made the conversion more like a walk in the park. Take the number of miles, say 40, then add half that number, and then 1/10 of it. And you get 40 plus 20 plus 4. So 40 miles was about 64 kilometers, an answer my father confirmed with the speedometer. I was so impressed. We tried her method with a few more imaginary destinations. What I learned that day was that maths was not just a set of rules that produced correct answers, but it could also be a tool to help me figure things out. And I could use that tool as I saw fit. In a way, 64 is the wrong answer, but in another way, it was as right as we needed it to be. My mother had used the same operations I was learning in school, but she used them as tools to suit her own purposes. She had not only rounded the troublesome conversion factor with a brash gusto I had not encountered in school, though very much admired, but she had also turned the 1.6 into a new thing, 1 plus 0.5 plus 0.1, that gave it new power, new usefulness. Okay, you can open your eyes now. So in terms of thinking about truth and truths and truths, what we argue in the book is that the right versus wrong dogma narrows mathematics down to a very mechanical calculation. Doesn't mean that there aren't situations in which things are not right or not wrong, but that there's more to math than just a focus on right and wrong. Right versus wrong expectations, as we know from the literature, produce a lot of anxiety amongst students when they know that there is one specific answer that the teacher is looking for, and they have very few tools for working on the question. Many students get so nervous that they actually have a difficult time thinking. And we know from the neuroscience literature that anxiety can really get in the way of thinking. So how do we de-emphasize right and wrong? How do we make that less the central part of what goes on in the mathematics classroom? I'd like to talk about 3 of the things that we discuss in the book. One is about appreciating how every fact is contingent. By that I mean dependent on a set of assumptions. About changing the kinds of questions we ask, and about inviting students into high feedback environments. So every fact is contingent. I want to give an example first of the kinds of things that we do in everyday in the classroom that you already know about, which is it's classical to use this example of 2 plus 2 equals 4 is just right or wrong, and that's the end of the story. So that's what math should be like. But of course, you've seen counter arguments. So 2 plus 2 equals 4 only when we are working in base 10. So that's the example of the contingency here, which is the fact depends on that assumption. 2 apples plus 2 oranges is only 4 if you want to know the number of fruit. But if you want to know the number of apples, it's 2. Or the number of kiwis, it's 0. So again, that articulates a certain contingency. And of course, from non-Euclidean geometry, we know the contingency of the idea that the sum of the angles of a triangle is equal to 2 right angles. So that only happens when our triangle is on the plane. And Alfred North Whitehead, who was a mathematician and a philosopher, was very adamant about the importance of understanding the contingency of all of our mathematical facts and the way that those can change if we change the assumptions, those facts, that is. So more generally, properties of objects depend also on their definitions. And this is not something that students usually encounter in school. They encounter the properties as if they were the right properties and not dependent on the objects and their definitions. And I want to give you a quick example of that. again, that will be familiar to you. I'm just going to pull up a little dynamic geometry tool. So this is something that I've done with kids at any age, starting from kindergarten all the way up to grade 8. So I've made a triangle here, and most students, if you show them this shape, will agree that it's a triangle. As you probably know, for many students, a triangle is actually what this looks like. And so if we move this around and present them with something, a shape like this, many students, even students in grade 3, will say that it's not a proper triangle, that it's some kind of upside down triangle. So here we see how they're not really aware of some of the properties, and this is a nice starting point for thinking about the relationship between the properties and the visuals. Also, a shape like this might seem for many students not to be a triangle. What I like about working in this kind of environment is that it enables us to see not only a whole family of triangles, and therefore to look at and focus on what is not changing as we drag this around, and therefore what the properties of the triangle are, but it also enables us to look at extreme cases, which are often what is most exciting about mathematics. So when I put my point down here, we have to ask, everything I showed you before was a triangle, but is this still a triangle? You probably have some strong feelings about it. Try to imagine arguing from the opposite point of view of what you believe. What kinds of arguments, what kinds of properties would we like to ascribe to a triangle that could make this a triangle or not a triangle? So if we say that a triangle has 3 sides, is this still a triangle? Does it still have 3 sides? So students might focus on things like, oh, well, it also has to have some kind of area, for example, or a triangle has 3 sides, but the 3 vertices cannot be collinear. So this pushes us into thinking about the contingency of the names of our shapes in this case and the properties that we want to give them. Okay. The second thing that Alf and I talk about in our book is the idea of changing the questions. So outside of the mathematics classroom, for any of you who are parents of adolescents, I'm sure you have had experience with the frustration of asking your child some questions and getting yes, no responses and not much more. So did you have a good day? Yes or no. Did you have homework? Yes or no. Are you hungry? Yes or no. So it's frustrating because as parents, we usually want to sort of get more information. And the problem is that these questions are geared towards just getting one type of answer, either yes or no. And analogously, this is what we do often in the mathematics classroom, is to gear our questions to just one type of answer, which is often, instead of yes, no, right, wrong. So what we propose is to go from asking questions such as what is 12 times 14, in which case the answer will be either right or wrong, to how do you work out 12 or 14? So to elicit different kinds of responses that aren't so obviously on one side of the binary or the other. So of course that demands a different kind of listening. So you're not just listening as the teacher for the right answer, but you have to listen with the student to understand how they are thinking about that multiplication. So of course it invites different ways of understanding as well from the student who might have different approaches to working out 12 times 14. We also talk about going from the question, how to respond to that question. So if a student responds that 12 times 14 is 108, which is a pretty frequent response for students who look at 12 times 14 as 10 times 10 plus 2 times 4. So instead of saying 108 is wrong, another response from the teacher could be 108 is the product of 12 times 9. So here the teacher is providing feedback to the student that shows how they're, what would be the correct answer, the correct question to the answer. So again, this is responding to the student rather than judging in terms of right or wrong. And another example of listening with. Okay, now I'd like to talk about the final example here, which is thinking about changing environments. So Alpha and I talk about moving from problem-solving environments to symbolically structured environments, and we give the metaphor, the analogy of tennis and squash. So I don't know if you're familiar with those two sports, but in my playing of tennis anyway, I hit the ball back, and often it goes over the back end of the wall, or not in the other court, or if I'm lucky, my opponent can't get it. So there's a way in which whatever it is rare that when I hit the ball back, I get anything in return. And so there's this openness to the tennis court that doesn't provide very much feedback and depends on one person. So in the analogy, that person would be the teacher on responding. In squash, you're in a big box, and no matter where you hit the ball, it's always going to come back, and it will be in a direction that respects the rules of reflection. So as you hit the ball in a certain way, it will vector off in a way that's symmetric. And so here we get a sort of more closed environment in which every move is responded to by some kind of feedback. And Alpha and I call those symbolically structured environments. So I'm going to, if you would like to interact yourself, please feel free to go to this URL. Again, tinyurl.com and dynamic quads. And if you don't want to, that's fine. I'm just going to look at this environment here. There are many, many, many different ways of thinking about symbolically structured environments. So my goal here is just to show you an example of one. We don't actually talk about this one in the book, so you can find some other ones in the book. But in this environment, again, which is in dynamic geometry, when I move one of the vertices of my quadrilateral, you'll see that the names that show up here on the right change over time. So you can think of me moving this as me hitting the ball. And as I move it, I get some kind of feedback from the walls about the name of this shape. And so all I am doing here is moving. So these are the rules of the game, is that I can move any one of these vertices, but I can also move a segment. And you can imagine the kinds of questions that we might ask. So how do we get a rectangle to come up, but not a square? So I can move this and I have a rectangle here. Is it possible to get a parallelogram and not a rectangle? Is it possible to get a rectangle and not a parallelogram? So here, the ways that I'm going to move my vertices become my ways of expressing the mathematical relationships and ideas. And of course, we can look also at things like the angles and the segments and the diagonals. But really, it's enough for the purposes of this talk and thinking about symbolically structured environments to just look at the names that are appearing here as I move these vertices around. Okay. So in this symbolically structured environment, you can see that the goal is very action-oriented. So the student is actually engaged in doing something. And it is that doing that creates the feedback that the student is experiencing. A feedback, by the way, that is not coming from a judgmental teacher who is saying right or wrong, but is coming from the environment and based on what the student has done. The symbols stand for actions or distinctions. So the goal isn't to teach the student what is a square, but for the student to look for distinctions that arise between the different names of the shape. So distinctions between square and rectangles that can be seen through the action. So in this case, the symbols, we can think of them in terms of the names of the shapes. And the rules for the symbol use, the names and some of the properties that I show you, do not need to be memorized. In order to engage with this environment, you don't have to know already what a square is or already what a right angle is. Those ideas emerge as you engage with the dynamic quadrilateral. There's a complexity that can be constrained. So we're not looking at all shapes. We're looking here specifically at quadrilaterals. But within that environment, novel moves can be made. So for example, a student who is who tries to move one vertex only and always maintaining a kite could be one of the novel moves that a student could make. So the point here is that in these environments, the emphasis on right and wrong is diminished quite a bit, and instead is on working within the environment, looking for patterns and relations where none of them are wrong, but each move is giving rise to a certain sort of distinction. So again, we have some images to help us think through this dogma, which we have identified as thinking in terms of binaries instead of pluralities. So on the left, we have a binary of right and wrong, which puts all of the weight on either one side or the other, with little opportunity for gray space and obviously little acknowledgement for the contingency of the facts. And on the right, we see this idea of other possibilities. So not just a binary, but a plurality. So when you're thinking, for example, about asking a question, what image do you bring to mind when you're asking that question? Are you anticipating that there's either one right answer or not? Or are you imagining that there's a plurality of answers? When you're thinking about designing questions or problems, are you thinking more in terms of the left image or more in terms of the right image? We hope these images work to become sort of things that you can easily bring to mind as you're working, both as researchers and as teachers. So some broader implications around these dogmas. As we know, mathematics learning has been characterized in many of these sort of binaries, that it's either abstract or concrete, either conceptual or procedural, either right or wrong, either objective or subjective, either reason or memory, symbolic or enactive, mental or embodied. We like to think as humans in terms of these binaries, and the problem with these binaries is that they overload each side of they put these ideas into one line where the endpoints turn out to have all of the important weight on them. And what also happens, as in many other binaries in society, is that one side ends up being seen as better, more important, more proper, more desirable than the other side. And so things that are concrete, procedural, subjective are all of a sudden seen as less good, which leads to a lot of struggle in mathematics for students as well as teachers. So instead of working within these dogmas of either or, we'd like to be thinking about mathematics as being both concrete and abstract, right and wrong, and so on, so that we move beyond some of the dualisms that have inhabited education for so long. And we see these images. Here are the two that Alf shared last week for thinking differently about the first two dogmas. And here are the two that I've shared this week. These images as sort of pushing on that binary thinking and offering other possibilities so that teachers aren't just left with one option of, do I do traditional math or do I do reform math, but can press on different possibilities for thinking about their mathematical practice. And with that, I'm finished.